All right, picture this. You're the on-call IT support engineer and your pager just went off. A critical payment has completely failed in the production environment. The catch? The error is buried somewhere inside a massive legacy database you've literally never seen before, and there's absolutely zero documentation. Welcome to The Explainer. Today, we're transforming into database detectives to tackle exactly this kind of problem.
It's a terrifying scenario, right? You're plunged right into the harsh reality of a live, high-stakes support ticket. You don't know the schema, you have no clue about the table relationships, and man, that clock is ticking loud while customers are seeing error screens. Every passing minute is lost revenue and growing frustration. You know you need to fix this fast, but where do you even begin your investigation when you are completely flying blind?
Normally, engineers might just pull the raw SQL data definition language, the DDL files, and painstakingly read through thousands of lines of text just to figure out how the tables are built. But contrast that painful, insanely slow text parsing with visual schema exploration using MySQL Workbench. For auditing legacy databases or just for rapid onboarding during an outage, visualizing the structure rather than reading endless lines of code is a total game changer. It's infinitely faster and way less prone to human error. Okay, step 1. Assess the database scope. Because before we even think about writing a single investigative query, we absolutely must methodically understand the sheer scale of the system. We definitely don't want to accidentally crash the live server, right? So, check this out. By simply right-clicking the schema in the Workbench navigator and hitting Schema Inspector, bam, we instantly get a bird's-eye view. We're aggregating crucial metadata for all objects in a flash. No queries needed, just a unified set of grids revealing everything about the Sequila sample database. It takes mere seconds to compile what would normally require dozens of individual show table statements. This right here is basically the ultimate engineer's checklist. We're checking row counts to gauge if we're hitting a few thousand or several million records. We're looking at average row length, index size, and checking for storage engines like InnoDB, which confirms we're dealing with transactional data that actually supports foreign keys. Think of this metadata as our early warning system. It tells us the exact scale and weight of the landscape we're about to query, so we don't accidentally trigger a massive table scan and take the whole system down. Now, digging a little deeper into the table inspector, we absolutely have to check the indexes tab. This reveals the cardinality and uniqueness across the schema, and guys, this is a vital safety check. If we're about to run some massive join query to find our payment bug, we must ensure those tables are properly indexed, because without knowing where the indexes live, our diagnostic query could time out, lock up the database, and actually make the outage we're trying to fix a whole lot worse. Moving on to step 2, build the schema blueprint. We've got the scale down, but to actually trace this failed payment, we need a map. To get that map, we fire up the reverse engineering wizard. It follows a strict 5-step protocol. First, we select our target instance. Then, we zoom in on the relevant modules. From there, the tool automatically queries the server's information schema to retrieve the DDL. Then, it parses that architecture and automatically maps all the foreign key constraints as relationship lines on a canvas. We are essentially translating raw, complicated server logic into human-readable geometry. And boom, just look at this map. This is our massive visual aha moment. What would have literally taken hours to mentally piece together from hundreds of raw SQL files is instantly mapped out right in front of us. Every table, every column, every relationship in the Sequila database is right here. Seeing the architecture visually represented like this is an absolute superpower when you're investigating an unfamiliar codebase under extreme pressure. But to actually use this blueprint, we need to know what we're looking at, specifically the line types. Solid lines. That means we're dealing with an identifying relationship. The foreign key is actually part of the primary key in the related table, meaning it's a very strict existential dependency. The dashed lines, on the other hand, indicate a non-identifying relationship, where the foreign key is just a regular column referencing another table. This tells us exactly how tightly our data points are bound together across the whole system. You know, the real beauty here is that Workbench handles most of this heavy lifting automatically. It maps out these incredibly complex crow's foot foreign key constraints for us, instantly showing exactly where one-to-many or many-to-many relationships exist. We don't have to sit there and guess how a user connects to a rental, and how that rental then connects to a payment. The software draws the exact path for us. All right, step 3, trace the failed payment. We've got our EER map, we know how to read the legend. It's time to actually squash this bug. So we can now visually trace the exact path we need. We start right at the payment table, which holds our failed transaction record. Following the visual relationship lines, we see a one-to-many link over to the customer table. That tells us who tried to pay. Following another line, we see a link to the rental table, which tells us what they were trying to rent. Instead of guessing in the dark, we now know the precise 3 tables we need to join to isolate that breaking constraint.
And just like that, the incident is resolved. Look at what visual exploration achieved for us here. We completely bypassed that painful raw SQL reading. We instantly gauged the system's massive scale, generated a beautiful visual blueprint of the entire legacy architecture, and traced the foreign keys to execute a highly targeted join query. It's fast, it's incredibly efficient, and it literally gives structure to chaos.
So I'm going to leave you with this question. The next time you are thrown into the dark trenches of a legacy codebase during a high-stakes on-call rotation, how are you going to audit it? Will you be stuck parsing text, or will you use your new reverse engineering superpower to map it out visually? Thanks for joining me on this explainer. Keep exploring, and I'll catch you in the next one.